and we have seen that what does our substructure code says, and which is the general philosophy also, that the open foundations we have to check for two conditions. What are those conditions?
Safe bearing pressure and safe bearing capacity.
That is one. Second,
from settlement point of view.
From settlement point of view, and from both, whatever is the lower value, that will be the allowable bearing pressure. So first we will see the bearing capacity. How do we calculate or arrive at bearing capacity? Now it will depend on type of soil. First, if foundation is in non-cohesive soils, cohesionless soil, sandy or gravelly soils, then the clause 6.3.1 of substructure code says that we can calculate bearing capacity by any of these methods. Plate load test, I am not going to repeat plate load test because it should have been covered in your geotechnical investigations, and you are all familiar that how do we calculate bearing capacity from plate load test, and some version of it will be covered later on also, so I am not going into detail. Then another is dynamic cone penetration test. This also I'm not going to cover in detail, and standard penetration test, SPT. These you all must be aware, and moreover some part or maximum part of this must have been covered in geotechnical investigation, so I'm not going into these details. How do we calculate bearing capacity by these methods? Fourth method it gives is from strength parameters, which is given in IES code also. So this briefly I will cover how it is to be done. This is what is given in IES 6403 1981. How do we calculate? So for this, if you recall, the classical theory of Tarjagi, which he gave regarding bearing capacity based on shear failure. If you remember, if this is your footing, if this is your base of footing, then he says there can be three type of failure: general shear failure, local shear failure, of a combination of that. And in general shear failure, if you remember, he says first at the bearing capacity or the load equal to bearing capacity, this footing will sink like a punch. There will be a sudden failure with some portion of soil in triangular. These angles are also given there, 45 plus or minus 5/2. These the dimensions it gives. This portion will remain part of the foundation, and then there will be two well-defined shear planes. Their geometry is also given, and then there will be heave on the surface here, something like this, and there will be a sudden failure that is called general shear failure. And another is local shear failure, where these planes are not very well defined. These planes are not very well defined. There is no violent or brittle failure, but slowly your foundation will start sinking into this, and you may not have these heave and all here. Clear, isn't it? Are you able to recall this? This must have been told in your UG and PG course. So based on this only, all this whatever the strength parameters and IS code is developed based on this theory only. So there can be three combinations. One is C5 soil, mixed soil, or you can have C type of soil, cohesive soil, or you can have only Phi type of soil. So for all three soils, the IS code says like this, and we have to follow it. Number one, it says the net ultimate bearing capacity. Please understand what is net ultimate bearing capacity. So it is QNF divided by factor of safety, net ultimate. How we can calculate? He says for now in C5 soil, it will be very difficult to determine whether the failure is due to general shear failure or it is because of local shear failure, and most of the time it may be a combination of the both. So therefore you calculate it for both modes of failure. First for general shear failure, and this QD, which is net ultimate bearing capacity, is calculated by this. If you see, there are first of all there are three parts of this equation. In this part, first part, this is stated to be due to cohesion, this is stated to be due to overburden, and this is the dimensional part, something like this. Or this is called C quotient, this is called Q quotient, and this is called gamma quotient. That is what we normally remember, C, Q, and gamma quotient. In all of them, in this first is C, which is cohesion. Here Q, and here 0.5 times B gamma. These are the first. C is cohesion value, Q is your pressure overburden, and 0.5 B is width of your foundation, and gamma is soil in filled up area, its density, in situ density. That is first thing. Similarly, and then there are second part, we will see second part also. Similarly for, or let us, see both. For local shear failure, this first portion of first quotient is 0.67 times C. This is Q only again, and here is 0.5 B. That is the first difference. Second difference is, if you see in all this, here there is NC, NQ minus 1 and N gamma. They are called bearing capacity factors. NC, NQ and N gamma are bearing capacity factors. And when you go to local failure, it is NC dash, NQ dash, N gamma dash. They are local bearing capacity factors. So NC, NQ, N gamma, NC dash, NQ dash or N gamma dash, or NC prime, NQ prime, N gamma prime are bearing capacity factors. And they are given in the IES code depending on phi value. Depending on phi value, you have value of NC, NQ and N gamma, and for phi equal to 0, NC is 5.14. That is, we always remember. That is for cohesive soils where phi equal to 0. And for local shear failures, or this NC, NQ, N gamma prime or N dash, whatever you call, what you do is you calculate phi dash, which will be 10 inverse of 2/3 of phi, or 0.67 of phi. And for this phi dash value, from here you get the NC, NQ, N gamma. So this is how you get bearing capacity factors from the IES code for local and general shear failure. Now in these equations, the next we have seen NC, we have seen NQ, we have seen N gamma. Next is SC, SQ or S gamma. Okay, and in this also SC, SQ and NS gamma. They are called as shape factors. It depends on shape of your footing. How is your shape of footing? And their values are also given in the IES code. For continuous strip, SC is 1, SQ is 1, S gamma is 1. For rectangular foundation, SC is 1 plus 0.2 times B by L. B is width and L is the length. Length is the longer dimension. Across that B is the shorter dimension. This also 1 plus 0.2, and here 1 minus 0.4 B by L. For square footing, 1.3, 1.2 and 0.8. And for circular footing, 1.3, 1.2 and 0.6. So these are the shape factors which is there in these equations. If you come after that, next is DC, DQ, D gamma. Here also DC, DQ and D gamma. What are they? They are called depth factors. So what does the code says? It says apply them only when your backfilling is done with proper compaction. See, if you remember, we have seen the difference between net and gross pressure intensity. So while taking net, you deduct gamma times depth of foundation waves. But it says you deduct that only when backfilling is done with proper compaction. This is properly compacted. If the soil is loose, you do not get this much advantage. You will lose this advantage. That is what it means. So the depth factor is like this: DC equal to 1 plus 0.2 DF by B multiplied by N phi. N phi is bearing capacity factor. DF is depth of foundation, B is width. DQ equal to D gamma equal to 1 for phi value less than 10 degree, and for phi value more than 10 degree, DQ and D gamma will be 1 plus 0.1 DF by B multiplied by under the root N phi, bearing capacity factor. So this is the effect of depth of your foundation that is captured in the form of depth factor. Next, if you see, the multiplier is IC, IQ, I gamma. In this also IC, IQ and I gamma. What is IC, IQ, I gamma? They are called inclination factors. Means if your load is not vertical. So if your load is not vertical and rather than being vertical, your load is in this direction and this angle from the vertical is alpha. In that case, these factors are IC and IQ are equal to 1 minus alpha by 90 to the square and I gamma is 1 minus alpha by 5 to the square. So these are IC, IQ, I gamma, and in fact whatever taken in IS code is there in every code of the world, and that is basically given by Tarjagi, and then Peck and these people Meyerhoff and these people, they have modified them. So world over this is what is followed. Okay, now there is one more thing which comes here, W dash in the third quotient. In the gamma component there is a W dash. What is W dash? Here gamma, as I told you, is bulk weight of the soil above the foundation. Q is effective surcharge at the base of footing, so gamma multiplied by df. Df is depth of foundation. W dash is to take into account the effect of water table. The same, if you remember table 6 also yesterday we have seen more or less same sort of thing. Here it says, let us say this is my foundation, this is ground level. What it says, if the water table is likely to permanently remain at or below a depth of df plus b beneath the ground level. So this is df, depth of foundation, this is width of foundation. So df plus b from the ground level means this much below the footing bottom. So if your water table is permanently likely to not rise above this, it will not rise above this, maximum it will come up to this level, it means its effect on the foundation bearing capacity will be very, very less, and therefore you take W dash equal to 1, means no effect, you are not reducing that third component which is contributing towards bearing capacity. Then it says if water table is located at a depth of df or likely to rise to the base of footing or above, so if your water table can come up to here or above, then you take W dash equal to 0.5. It means the third component of bearing capacity part in equation becomes half. Same thing if you remember yesterday in table 6 also it was given, if water table is likely to come to the base of foundation or above, you reduce the bearing capacity by half. That is what was given there. And if water table is likely to remain in between, we have seen this full for this 50% reduction, then it says you do linear interpolation and find out the value of W dash. Okay, so this is clear how this equation of bearing capacity, what are various components, and from there where you get those values.
सर ये जो अभी bearing capacity factors जो बताए थे, लोकल शेयर फेलियर के केस में सर वो पाई का फॉर्मूला एक बार वापस दिखाएंगे.
In case of local shear failure, phi dash you will take equal to 10 inverse 2/3 of phi, whatever is your phi value, and treating this as phi value, then you will get NC, NQ, and gamma. That will be NC dash, NQ dash, and N gamma dash.
सर ये 10 इनवर्स 2/3 of phi होगा या 10 इनवर्स 2/3 of 10 phi?
10 inverse 2/3 of phi. Sorry. 10 inverse, 10 inverse 2/3 of phi. Yes. Must be 10 inverse of 2/3 of phi.
So 10 phi होगा सर.
So 10 inverse 10 of 2/3 5.
Just wait. It's 10.5. 0.67, 10.5. Yes. Yeah. 0.67, 10.5. Correct. Yes. Anything else?
No, sir.
Any other question or doubt about this equation and how do we calculate the bearing capacity from this? No? Okay. Then how to account for effect of eccentricity? Now eccentricity can be expressed in three terms. One is, this is your center of footing, but your load transfer is here. It is not at the center. So you have eccentricity Ex and Ey in X and Y direction. In that case, using that Beer-Hobbs formula, you consider width equal to B minus 2Ey and length equal to L minus 2Ey. This is Ex, sorry, this is 2Ex. This will be 2Ex and this will be L minus 2Ey. So this area will be neglected and you will consider only this much width of the footing, and then you will calculate whatever footing pressure and all, and you will check it is less than your bearing capacity. And secondly, the eccentricity can be in terms of moment, X and Y moment. Some moment may be getting transferred. In that case, we can convert moment into eccentricity. Ex will be My divided by Fv and Ey will be Mx divided. Fv is vertical force. So we can convert into eccentricity and again apply the same principle. Third thing can be eccentricity is because of application of some horizontal load. Here on your footing, some horizontal load is being applied. So let us say that horizontal force is Fhx or Fhy. So Fhx you multiply it by the lever arm from the bottom of this, that will give you My, and you apply the lever arm to Fhy, that will give you Mx. From this you calculate the Ex-Ey, and from Ex-Ey you calculate the effective area of the base of your footing where your load is getting transferred, and consider this much area only. So this is how you take into account the effect of eccentricity of the load when load are not centric. This was for C5 soil. Now for cohesionless soil, let us say where C equal to 0 and only phi contributes to this. There, for cohesionless soils, first we try to decide about the mode of failure, and mode of failure is decided based on relative density or density index, as we have seen in our earthwork classes, how to calculate density is a gamma max, gamma minimum, and your actual gamma and the side. So it says if relative density is greater than 70% or void ratio is less than 0.55 in dense condition, and you are likely to have general shear failure. So you can take the formula of general shear failure. If it is less than 20% or your void ratio is greater than 0.75, then it is in loose state and you are likely to have local shear failure or punching shear. So you take formula for local shear failure. If your value is between 20 and 70% or your void ratio is between 0.55 to 0.75, it will be in medium state, and then you interpolate between them. Take between both of them and based on your actual value, you interpolate. That is what it says. First, decide the mode of failure, and then the ultimate bearing capacity will be using this equation for general shear failure and this equation for local shear failure. And here the only change from previous one is your first component of the bearing capacity, which was the C component, has been eliminated. That is the only change. Otherwise these equations are same because your C value is 0. So with this, and now depending on what type of failure is there, maybe either you take this or you take this or you interpolate between both of them. So this is for C equal to 0 or granular or cohesionless soil. Yeah, for cohesionless soil. Another thing, for cohesionless soils, you can also calculate it based on your SPT test N values, the corrected N values. And how to do is given in the code. It says first you determine the n values at an interval of 75 centimeter. Please note, normally we do n value test at 1.5 meter. For this purpose, if you want to use, determine n value at every 0.75 meter in vertical direction or wherever there is a change of strata, whichever is earlier, and take the average of all the n values. Let us say this is your footing. So start n value from base of your footing to the depth equal to 1.522 times b. In this range, you calculate n value or find out n value at every 75 centimeter. Then take their average values. That will be average n. Then you refine these n values. There may be some error, there may be some aberration somewhere. So if any individual n value is more than 50% of the average calculated, then that value shall be neglected and recalculate the average. So like that, calculate the average, refine the average to take out anything which is, obviously there is something wrong in that value. And from this n value, you get the phi value. Chart is given in the IES code. This is your n value here, 80, 70, 60. So let us say your n value is coming 30. This is your phi value, 36. So you get phi value for your footing, and then using this phi value you get whatever NC, NQ, N gamma and all those things, and calculate the net ultimate bearing capacity using the equations which we have seen as per IES code. So this is if you are using standard penetration test results for calculation of bearing capacity. That is for cohesionless soil. Now C5 value, either you do the test, shear test, direct shear or triaxial shear, depending on what conditions you are simulating. If you don't want to do that, then from n value you can calculate phi value, and then from phi value go back to those calculations. Okay. So C5 soil, phi type of soil. Now I come to C type of soil, where phi equal to 0, cohesive soil, clay soils, maybe sometimes silty soil also. For them, if it is a homogeneous layer, means the layer below footing is homogeneous. Now the question may come up to what depth it must be homogeneous. It should be homogeneous. I don't know whether it was covered. It must have been covered up to significant depth. What is significant depth?
Sir, 1.5 to 2b. Sir, the depth up to which the effect of settlement effect will be transferred.
So normally that is called 10% isobar line, 0.1 Q line. You put the isobars. In fact, this is the theoretical thing world over. It gets covered in geotechnical investigation. It does not matter. In normal soils, it is up to you plot this pressure bulbs, 80%, 70%, 60% using Bussinesq or Westergaard or whatever theory. So the 10% isobar, 0.1 Q, is normally significant depth, and for weak soils or cohesive soils, you go up to 0.05, 5% isobar. So up to this isobar, that depth, if it is same type of soil, then that is homogeneous layer. That is what you do. So for homogeneous layer, here you have only taken the first part of your bearing capacity equation. Other two parts, Q and gamma part, you have eliminated, and C, NC, SC, DC, DI all, and NC value, as I told you, for phi equal to 0 is always 5.14, and other things you determine from those charts and tables and all, and you calculate net ultimate bearing capacity. This is when it is a homogeneous layer. But rather than homogeneous, let us say it is two layer. First we will see two layer, then same formula you can convert 3 to 2 to 1 like that. In case of two layer, here let us say this is bottom of your foundation, this is first layer, its value is C1, and then bottom layer C2. Normally as you go down, your C value decreases, your soil becomes more granular. That is what normal, except few areas we have got lateritic soils and all. Right, this is the general pattern. So this is value C1, and this is C2. In fact, of course, this covers both condition, this chart. So if you have got two layer system and it does not mark anisotropy, anisotropy means in different directions, your value of C is not different. Let us say you take a core by drilling in perpendicular to this and calculate phi, and you take core like this and calculate phi. It must give the same value. So your soil should not be anisotropic. Then it says you can calculate the ultimate bearing capacity, net ultimate. Rather than C, you will use a value C1. Other all components are same, NC, SC, and C1 you get it from this chart. The C1 value you get it from this chart. How is this chart? On this chart, this side is your C2 by C1. C2 is C value of second layer and C1 is C value of first layer. It can be less than 1, it can be more than 1. Then there are further charts which are based on D by B. B is your half width of the foundation when it is vertical. If it is eccentric, then you will reduce that width and take half of that reduced width. And D is your thickness of this layer, thickness of first layer. So D by B you will calculate, and then you will calculate C1, C2, and you will see whichever is appropriate this thing. And for that, actually it is an NC, this value, yeah, NC, this should be NC1, C1 into NC1 or NC. NC value, rather than taking 5.14, you will take this value. So these are the NC values. So let us say your C2 by C1 is 1.2 and your D by B is 0.2. Then this will be your chart, and your NC1 value will be 6 point something, 6.2 or 6.1. So that NC value you will take, and you will use the cohesion value of the first layer. Same formula you can apply for it. A 3 layer, first convert 3 to 2 and then 2 to 1 normally, but in practice people what they do is they take weighted average and convert into 2 layers. That is what is done even for calculation of settlement. So this is for 2 layers, and that was for homogeneous layers for cohesive soils. So this is how, when your strata was mainly on cohesionless soil. Now let us say your foundation is on cohesive soils. In that case, of course, we have covered cohesive also some part here, so that will be used here. If it is on cohesive soil, then 6.4.1 says same as you do for cohesionless soil. There is not much of difference. That's why if you see previously in cohesionless, we have covered the cohesive soil case also. C5, C and phi, all 3 type of soil. Same approach is to be followed for cohesive or non-cohesive. Only paras are given differently. That's the difference. Okay, so this is about when your foundation is on soil. How do you calculate the bearing capacity? And presumptive bearing capacity, or for small foundations or for unimportant cases, you can use table 6 of substructure code also. Clear?
Yes, sir.
Now
Yes, sir.
come to rocks. Let
Yes,
us say
sir.
foundation is on rock, what is to be done? And please understand, again I am reminding you, these all provisions are of substructure code. So these provisions will apply, of course, most of the places they are referring to IS code, but strictly speaking, these provisions will apply for bridge foundations. Please be very, very clear. When you are using this for building foundations, please refer to the relevant IS code. And if there is some difference between IS code and substructure code, then provisions of IS code will prevail and not the substructure code. So be very clear. What we are talking is foundations in terms of bridges. So now foundation on rock, what is to be done? It says number 1, it shall be designed taking into account nature of rock formation and other geological features like dip and strike of the rock, presence of fault and fissures. When we were talking about tunnels, if you remember last time, I said there are various features in rocks, dips and strike, presence of fault, in what direction it is dipping, it is striking across or striking in the perpendicular plane. So all this have to be taken into account for deciding the bearing capacity, which is a bit complicated than soil. And your foundation should not rest on faulted strata likely to slip. If your strata is like this, your fault level is like this, you must avoid resting your foundation here, otherwise it may slip, or otherwise you have to give some anchorage arrangement and all those sort of things. Then fissure strata, if you have got heavily cracked or fissured strata below your foundation, do the grouting to fill up those cracks and fissures and strengthen them. And then it says the ultimate bearing capacity. Here word is ultimate. There in equations it was net ultimate. So please be very careful about these terms. It can be taken as 4.5 times the unconfined compressive strength. If you remember in slope stability, when you were in phase 1 we were talking, one of the tests for determining shear parameters is unconfined compression, where you can make a cylinder of the specimen and it can withstand without any lateral support. You apply the load and it fractures at this, it cracks at some angle. So whatever is QU, you take that and CU will be QU by 2. So it says ultimate bearing capacity, which will be QU in this case, can be taken as 4.5 times the unconfined compressive strength, and this should be determined by taking a test specimen of 4 cm dia and 10 cm height, L by D ratio 2, 5 cm dia and 10 cm height. You take a core of the rock. If rock is in such a condition that you can take a good core, take a core, do unconfined compression test, which is very common in case of rocks incidentally. And then it says, now you have to finally find allowable bearing pressure. In rock, calculating settlement is normally not done, calculation of settlement. So for allowable bearing pressure in sound and homogeneous rocks, let us say your rock is sound and homogeneous, then you use a factor of safety of 3. So whatever you have found out from here, 4.5 times, apply a factor of safety of 3, means effectively it becomes 1.5 times the unconfined compressive strength. That is what it comes out. Then for other rocks, let us say your rock is not very homogeneous, it has some joint, then factor of safety is a matter of engineering judgment depending on extent of weakness. It is very weak, we go up to 6, you may go up to 3.5 or 4. So it is a matter of engineering judgment, how much factor of safety we must apply. That was for mostly homogeneous rocks. Now let us say your rock is non-homogeneous or unsound, highly fissured, weathered, cracked. There it says that a factor of safety of 6 to 8 on unconfined compressive strength should normally be adequate to cover such rock deficiency. So here between 6 to 8, very high factor of safety because your rock is not homogeneous. There are other discontinuities in that. And then it says if rock is so badly disintegrated or it is so soft that you cannot take the core recovery is found to be less than 35%. When you take a core, let us say total length you have driven L, same concept you use in RQD also, and finally core you recover of some length L, then L by maximum core above a size, L by L is your core recovery. So if your core recovery is less than 1/3, it means it is highly disintegrated you are getting, or it is not even possible to make the test cylinder of that size, 5 cm dia and 10 cm dia. Then what you must do, it says the allowable bearing pressure may be assessed by adopting methods prescribed for soil. So for soil, what is the method prescribed? Do direct shear test or triaxial shear test, find out the C5 values, then calculate by using those equations given in IS code. So if your rock is highly disintegrated, treat it as soil and determine the allowable bearing capacity or whatever bearing pressure. Otherwise, for homogeneous rock, factor of safety 3, for non-homogeneous rock, factor of safety of 6 to 8 over your unconfined compressive strength. Okay. Okay. So first part, I hope it is clear now that how do we calculate the bearing capacity in case of open foundation. All it is in context of open foundation.
Yes.
Right.
Yes.
Okay. Now go to settlements, because as we said, from both considerations, settlements and oblique or differential settlements. What do we do there? So there, first, non-cohesive soils means cohesionless soil, sandy or gravelly soils, soils having high phi value and almost 0 or very low C values. In these soils, we have seen this in earthwork also, that your settlement takes place very quickly. The moment you apply the load, your settlement will take place, which we call immediate or elastic settlement. And it is over for dead loads during construction stage itself. During construction itself, whatever is settlement which is likely to happen for dead load, because dead load has been applied during construction stage. So dead load settlement is already over by the time your construction is over. After that, whatever it means before you place your or for girders also, if you take immediately after placing girders, only live load settlement will happen after that. So for such type of soils, for settlements, various methods are given. First is based on SPT. If you have done SPT, it can be done. How? It says that settlement per unit intensity of pressure can be obtained from the chart. There is a chart where settlement per unit value of Q can be obtained by this chart. Now this is the chart. In this, V is vertical load, B is bottom width of the footing, D is depth of the footing, small d is water table below depth of the footing. Okay, and this is the chart given. In this chart, if you see, this side is settlement per unit pressure in kg per square centimeter. This is settlement value. This side is width of the footing, and there are various charts for different n values. Now let us say your width of footing, just let us take 3 meter, n value is 15. So for this will be your settlement. This is in logarithmic scale. So 0.09, 10 to the power minus 2. So 0.001, 0.01. So yeah, this is 0.09. This will be 0.09. It is 0.09 meters per kg per square centimeter pressure. So now whatever is your pressure for that, whatever is your load intensity for that, you can calculate the settlement. This is one approach. Then over this settlement, you have to apply some correction factor. What is that factor? For location of water table, if water table is a shallow depth, the settlement shall be multiplied by correction factor W dash, and W dash, this is your this is a line, this is D by B. D is depth of water table below the bottom of your foundation, B is width of your foundation. So this side is D by B value. Let us say D by value is 0.4. Then you come here and your correction factor is 0.7. And as you can see, when D by B becomes 1, your correction factor becomes 1, means no reduction. So when it is B below this, no effect, as we have seen all along. And when it is above that, this is how you calculate. And maximum value is 0.5. When D by B is 0, means your water table is touching bottom of foundation, you can see this value is 0.5. Same thing as we have seen previously twice. So this is settlement, one way of calculating settlement when foundation is on non-cohesive soil and you have got data of SPT tests with you. Second is you have done plate load test. Now after doing plate load test, as you remember, you plot load or stress pressure versus settlement curve. So you will have a load versus settlement curve with you in plate load test. So here it says that settlement for footing. Now this is settlement for plate, settlement of the plate. Now here let us say this is my pressure and this is settlement, and my permissible settlement is 25 mm. This is for plate. First I will convert it to settlement of footing, and then for that value you will read your pressure. So you will know how much is the bearing capacity from settlement point of view. And this is the conversion formula. Settlement of footing in mm is calculated by this formula. SP is settlement of plate. From that chart we can take. BF is width of BF is size of footing, width of footing, and BP is size or width of test plate. BP is size and width of test plate. So we use a square plate this size. So this is if you want to use results of plate load test for calculating settlement, or other way around. What you can do here is you don't actually calculate settlement. For your maximum permissible settlement, you try to find out what is the load intensity or pressure which you can take. And then for fine-grained soils or cohesive soils, predominantly C type of soil where phi value is 0 or very close to 0 and its strength comes from C type of soil, clay, silty, that sorts of soil, clause 6.4.2 of substructure code is used, and it says in this it is bit involved exercise, because here, as you remember, there will be consolidation settlement. In your fine-grained soils or cohesive soils, there is a consolidation settlement. So here what happens is, initially let us say this is your ground level, and we just assume, let us say 2 or some layer, there are 2 layers below this, and 2 layers, when I am talking 2 layers in the significant depth, always be clear about that. So under dead load there is an equilibrium, there is no problem. Now the moment I apply live load, now live load due to anything, maybe due to footing, through footing, or whenever I apply extra load, which may be load of footing or live load, then initially there will be some pressure here. Let us say at the center of this layer the pressure is P0, which will be what? Gamma times this depth, whatever is this depth, D1. Or if we talk about this layer, it will be this layer's gamma times whatever, gamma 1, if this is D11, whatever you can take, and this layer's gamma 2, D2, whatever value, this overburden pressure basically, that is initial pressure P0. And it is in equilibrium at that time. Now when you apply extra load, what will happen is the water here will develop pore water pressure and it will try to squeeze out, and this pressure P0 will increase by delta P. And how it is increased, you can take a distribution like this, you can take Westergaard or Businesq or Osterberg chart. There are various methods of finding out influence of this at different depths. By using those methods, you will find out that how much it is increasing at center of every layer. Where initially it was P0, it will increase by delta P. And because of extra pressure, underwater pressure, this water will try to ooze out, and in that process there will be settlement. So that is basically consolidation settlement. So settlement should be computed for dead load only, that is number 1, it says. Then it says the total settlement in this case will consist of 3 parts, PI, POED and PS. What they are? PI is immediate or elastic settlement, which is due to compaction, like same earlier one, and there is a equation for calculating PI. Then P audiometric is primary consolidation settlement due to consolidation. This is because your water is going out from your pores because of extra pore water pressure, additional pore water pressure being developed. So that much space there will be settlement. And the consolidation settlement, there is also something called secondary consolidation settlement. In addition to water going out, there is a readjustment, there is a rearrangement of soil crystals within the soil or soil particles. That also causes settlement, that is called secondary consolidation settlement due to adjustment of internal structure of soil mass during consolidation. And how it is calculated? PI is calculated in same manner as for cohesionless soil, elastic. So we have seen in cohesionless soil how settlement is calculated either by N value or by plate load test and all. That is your elastic or initial settlement. So here also in the same way as you have done for cohesionless soil. And for calculating P audiometric or primary settlement and secondary settlement, as I told you, first calculate the initial vertical pressure for any layer of substrata. So if you have got 2-3 layer, for every layer, what is the initial pressure? For every layer P0 we calculate before application of footing and this other dead load. Then you also calculate increase in this pressure due to load application, which is due to construction of structure, by using any suitable method. As I told you, Businesq, Westergaard, Froelich, so many, Osterberg, there are various people. So you calculate P0 and delta P for every layer. Layer 1, layer 2, this may be P01, this may be delta P1, delta P2. Calculate this, and then there is a formula for calculating primary consolidation settlement or audiometric settlement. HT divided by 1 plus E0 multiplied by CC multiplied by log to the base 10 P0 plus delta P divided by P0. Here P0, as I have told you, initial vertical pressure at the center of layer. Delta P is increase in vertical pressure due to construction of structure. HT is thickness of that layer, first layer, second layer. Every layer you will calculate this value separately. P audiometric 1, P audiometric 2, 3, like that, whatever layer. E0 is initial void ratio of that layer, which gets measured in as part of your consolidation or audiometer test. And CC is compression index, which is again measured in your audiometric test or consolidation test. So like that, you calculate primary consolidation settlement for each layer. Add all layers primary consolidation settlement up to significant depth, means 0.5%, because this is cohesive soil. So 5% or 0.05 pressure bulb. Then secondary settlement also. Now, if this increase, if this load increment delta P is more than PC minus P0, PC is pre-consolidation pressure, the pressure to which soil has been subjected, the maximum pressure in the past, as you know. So that is also you work out from consolidation test charts. So if your load increment which you are applying delta P is more than PC minus P0, then you calculate secondary consolidation by this formula. Then this is also done for every layer. And if your load in PC is pre-consolidation pressure, E is thickness of clay layer, whatever was HT here, word E is used. And if load increment is smaller than PC minus P0, then this is the formula for, because here there will be recompression, here there will be virgin compression, that's the difference. So PS by C0 plus 1 plus E0 E log 10 PC by P0 and PS equal to CC plus this. You calculate the secondary consolidation settlement for every layer, and now you add primary separately for every layer, secondary separately. So you will have total primary or audiometric settlement and total secondary and audiometric settlement. So add them to the initial settlement and you will get the total settlement. Okay, so now I hope settlement calculations, how they are then, they are clear. Cohesionless soil and cohesive soil. Cohesive soils, it is bit more involved. Cohesionless soil, it is easier. Okay?
Yes.
Now there are some corrections which are applied for depth and rigidity of the foundation, again given in IS code. First is to settlement. First is effect of depth of foundation. Now this settlement calculations are all assuming that foundation is at ground level, but your foundation will be having some amendment into the ground. So for foundation at utter depth, apply the correction factor as given in the chart. This is the chart given. D by under root LB or under root LB by D, whatever factor. D is your depth of foundation, B is width of footing, and L is its length. So you calculate this. If you calculate D by under root LB, it will be less than 1, or if it is other way around, if under root LB by D is more, less than 1. So this is 1. This is medium position there. Then these various graphs are for various L by B ratio, L by B 100, L by B 25, L by B 9, L by B 1, like that. So for your case, whatever, let us say your D by under root LB is 0.4. So we come here and L by B is 25. You come here, go here, it is some 0.81 or 82. That is your depth factor correction. So you calculate that and multiply it to the settlement. That will be your correct settlement. That is depth of foundation. And second is effect of depth of rigidity. Here we are assuming foundation to behave elastically as a full elastic element, following your Euler's theory of bending or whatever. But so if it is not the case, then if foundation is rigid, in case of rigid foundation like heavy beam and slab raft or massive pier, on that it may not behave exactly in an elastic manner. In that case, you apply the effect of rigidity and the total settlement should be reduced by a rigidity factor equal to 0.8. So these two factors you will apply over the settlement, depth of foundation and rigidity of your foundation. and that gives you the actual settlement. Now coming to permissible settlement values. Now, as I told you, it depends on your type of, normally like railways, we take 25 mm total settlement. And then we have seen in case of simply supported structures, you can increase. In case you can correct the girder level, you can increase it like that. So just to give you an idea, this is the table 1 in IES 1904. Of course, this is strictly speaking for buildings. This is not for bridges. This is only to give you an idea how much can be the value of this. For bridges, you have to decide on case to case basis. This gives you permissible settlement for isolated footings, for raft footing, then again for sand and hard clay, plastic clay, sand and hard clay, plastic clay. Everything gives maximum settlement, differential settlement, and angular distortion, because angular distortion is more important. If your structure is very long, even small differential, a large settlement will calculate angular, whereas in small one, even small will create more angular distortion. So all these three values are given. And it is for like for steel structures, these are the value 50 mm, differential settlement of 0.0033 times L, 1 by 300 is angular. This mm is written wrongly in IS code. In fact, in angular settlement distortion, there is no unit. It is 1 by 300, 1 by. So 50 mm is general for steel structure, for RCC concrete structure. For multi-story building, RCC or steel framed 60 mm. For load bearing wall 60 mm, for water towers 50 mm. You can get an idea at least what ranges these settlements are there. Not exactly, it is not applicable mutatis mutandis to the bridges, but you get an idea what range your total settlements and all are there. So this is a table from IS code. So this was about settlement. We have seen about bearing capacity, we have seen about settlement, and idea about how the settlement and differential settlements are expressed. Clear up to here? No doubt?
Yes, sir. No doubt.
Okay. Then last 1 or 2 slides, which is again typical for railway bridges. In other codes, things may be like different. This is some sort of relief which you give to permissible loads or something when you check for combination of loads. So see, there can be many type of load: wind load, earthquake load. In India, of course, we don't calculate. We also maybe if you go to J&K and all, or in northeast some places, Tawang or somewhere where railway line is going now, snow load. All these things, all adverse things may not happen at the same time, right? Whereas we take all the loads or their combinations. So taking that probability factor that every load may not happen at the same point of time, you give some relaxation when you check for combination of load. So this is what first is clause 6.7 of substructure code. It is about allowable bearing pressure, and it says when we are checking for combination of loads, the allowable bearing pressure can be increased as follows. So whatever allowable bearing pressure which is coming from theoretical calculations, allowable means taking into account settlement and everything overall, you can increase. Increase for what? 3 combinations are given. Combination is you consider all loads except wind and seismic load. You calculate for considering all the loads except seismic and wind. In that case, you don't give any extra margin. Your allowable bearing pressure will be allowable bearing pressure as calculated. Combination 2 is all loads including wind but excluding seismic forces. You have taken effect of wind into account, and all worst combination of your tractive force, braking force, which probably next week it will be covered when bridge code, our railway bridge code is bridge rule when it is covered next week. They will tell you that what are various loads. Everything you will take, and you will take wind also, but you will not take seismic force. In that case, you can increase 1/3, 33.3%. And worst and third combination is all loads including seismic but excluding wind. Normally you will see seismic and wind both are not taken because you don't consider the maximum wind also will come at same time and maximum earthquake also will come at same time. That is very rare. So it is including seismic but excluding wind. Then you can increase by 40%, 1.4 times your allowable bearing pressure. That is what our code allows for allowable bearing pressure. And for condition of stability, if you want to check factor of safety against stability or something, Then it says following factor of safety shall be ensured for stability under combination of loads and forces against overturning. Let us say you are checking against overturning some stability of the structure. Then for combination 1, 2.0 and combination 2 and 3, 1.5. This factor of safety you must consider. And when you are considering against sliding, normally open foundation, you check in addition to bearing capacity, you also check against overturning or sliding, that they should not overturn or sliding. So for overturning, this factor of safety, and against sliding, for condition 1, factor of safety 1.5, and for combination 2 or 3, you can take 1.25. These are the factor of safety for various conditions of stability. So this is combination of loads. When you take, you give some relief in your bearing capacity or something by taking the probabilistic consideration. That's all. So with that, we have covered the open foundation. As I told you, I am not going to cover the construction part of open foundation. Well, that's very simple. It is a simple RCC or masonry or CC structure where you don't need to be told. Whereas in pile and well foundation, you may not be much familiar about their construction aspects also. So we will cover that also in pile and well. Okay. So any questions before we break for tea?
No, sir.
No questions? Everything is clear?
Yeah.
पूरा साफ है या बिल्कुल साफ है?
सब रिटेन तो नहीं कहने सर, बट सब समझ आ गया सर.
And the concept, as I told you, you can always refer कि factor 1.2 था कि 1.5 था, even I don't remember. But you must know कि what is the concept given and where it is given. Where will you refer it? If these two things you understand, probably, maybe for exam, few things you may have to remember, that also not much. But otherwise, you must understand the concept of working out various parameters.
Yes, sir.
Right, good. Okay, then, if there are no questions, you can have your tea break. And after tea break, whatever is your class, please join that. Okay?
Okay, sir. Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Bye.